Welcome to the another lecture of this course, Computer Aided Power System Analysis. We have been discussing the Newton-Raphson load flow in the rectangular coordinate. So far we have been discussing, we have discussed that in the Newton-Raphson rectangular coordinate, the equations of load flow can be represented by this delta x delta m, where matrix J is constituting of 6 submatrices J1, J2, J3, J4, J5, J6. Vector x, that is the correction vector, is constituting of 2 subvectors delta E and delta F, and delta m, that is the mismatch vector, is constituting of 3 subvectors, that is delta p, delta q and delta v square. Now, we have been also looking at the expressions of all the elements of this matrices J1, J2, J5 and J6. So, to define this matrix J completely, we also need to find out the expressions of the elements of the matrices J3 and J4. So, today initially you would be doing that. Now, matrix J3 is essentially, we know that it is actually del q by del E, because from here we can see that matrix J3 is actually connecting delta q vector with the delta E vector. So, it would be delta q m plus 1 by delta E 2, delta q m plus 1 by delta E 3 dot delta q m plus 1 by delta E n, and then up to, we will go up to this delta q n by delta E 2, delta q n by delta E 3, then delta q n by delta E n. So, this is the structure of the matrix, and we have also seen that the dimension of this matrix should be n minus m cross n minus 1. So, this is a rectangular matrix. So, then therefore, according to our own parlance, it will have something called self term, where it is delta q I by delta E k for I is equal to varying from m plus 1 to n, k varying from 2 to n, and k is equal to I, and we say that it is non self term it is again denoted as this delta q I by delta E k. The conditions are same, the range of these different indices are same, only difference is that now k is not equal to I. So, now therefore, you have to now find out these expressions. So, to do that, we need to look at the expressions of q, what we have already defined or rather derived. So, the expression of q is given by f I into E k g I k minus f k b I k. So, we have q I is k is equal to 1 to n Fi into Ek, sorry, Ek Gik minus Fk Bik, then Ek Gik minus Fk Bik minus Ei Ek Bik plus Fk Gik minus Ei Ek Bik plus Fk Gik. So, this is the expression. Now, as before, we will take out the ith term separately. So, then when I make k is equal to I, so what becomes? This becomes Fi Ei Gii, and this becomes minus Fi square Bii, and this becomes minus Ei square Bii, and this becomes minus Ei Fi Gii. So, then therefore, this Fi Ei Gii and this minus Ei Fi Gii will cancel out. So, what will remain is basically minus Fi square Bii minus Ei square Bii. So, if I do take them together, I will get, that is Ei square into Fi square into Bii plus k is equal to 1 to n not equal to I, then Fi into Ek Gik minus Fk Bik minus Ei, that entire expression Ek Bik plus Fk Gik. So, this is the expression. So, now we first do the non-self term. So, non-self term would be delta Qi by delta Ek, k is not equal to I, and we have already written the ranges of I and k here. So, then therefore, we are not really repeating them unnecessarily. So, that should be equal to, so now of course, this particular term would be 0, that is if I do take the derivative of this term with respect to k, that would be 0, and in this entire expression there will be only one term which will have Ek. So, it would be Fi Gik, and this would be 0 and minus Ei Bik. So, it would be Fi Gik from this Fi Gik minus Ei Bik. So, that would be the expression. This would be 0, this would be 0. So, non-self term is this. Now, go to the self term. So, self term, so self term is again delta Qi by delta Ek, k is equal to I, and we have already written the range of this I and k. So, then therefore, we are not really repeating them. So, that would be equal to delta Qi by delta Ek is. So, from this minus 2 Ei Bii, so minus 2 Ei Bii plus k is equal to 1 to n not equal to I, and I am trying to do it with respect to Ei. So, then therefore, this term would be all cancel out. So, only this term will remain. So, EI, so minus EK BIK minus FK GIK. So, it would be minus EK BIK plus FK GIK. So, then therefore, what we have is delta Qi by delta Ek for k is equal to I. So, that would be equal to minus 2 EI BII minus k is equal to 1 to n not equal to I Ek BIK plus Fk GIK. So, this is the self term. So, this is the self term. So, this is the self term for J3. So, this is the self term for J3 and this is the non self term for So, now only one Jacobian submatrix is now left, J4. So, let us do that J4. J4 is equal to del Q by del F. So, it would be again del Q m plus 1 by del F2 del Q m plus 1 by del F3 dot 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 del Q m plus 1 by del Fn. It would go up to del Q n by del F2 del Q n by del F3 and it would be del Q n by del F n. So, again its dimension is again n minus m cross n minus 1. So, it again it is a rectangular matrix. So, it will have a self term it would be delta Q I by delta F k. I varies from m plus 1 to n, k varies from 2 to n and k is equal to I, and then as usual non self term is again delta Q I by delta F k. Again I varies, the range of variation of I and k are same, only difference is that k is not equal to I. So, then therefore, we now derive this. First we derive the non self term. So, we derive first non self term. So, non self term is del Q I by del F k with the condition that k is not equal to I. So, that would be equal to, if we go to this expression, we are now trying to take the partial derivative of this expression Q I with respect to F k, where k is not equal to I. So, this term would be 0 and I will get, we will get one term from this, that is minus F I B I k, and one term from this, that would be minus EI GIK. This term also would be 0, this term also would be 0. So, it is minus FI BIK and minus EI GIK. So, it would be minus FI BIK plus EI GIK. So, this would be the non-self term. So, we write it. So, this is non-self term for matrix 4. Then the last one is self term. So, self term is del Qi by del Fk with the condition that k is equal to I. So, that would be equal to. So, first is that we have to take the derivative with respect to Fi, because we are actually taking the partial derivative of Qi with respect to Fi. So, from here I will get 2 Fi Bii minus, that is. So, it is minus 2 Fi Bii plus k is equal to 1 to n not equal to I. So, we are trying to do it Fi. So, only this much Ek Gik minus Fk Bik. So, Ek Gik minus Fk Bik. So, that would be the self term. So, we this is actually self term for So, now we have essentially derived all the elements of this Jacobian matrix J, and now we are in a position to describe the very basic skeleton algorithm of the Newton-Raphson rectangular technique. So, therefore, we write basic algorithm of, once we understand the basic algorithm, then we would be in a position to understand the algorithm which converts everything for NRLF in rectangular. So, the steps would be steps 1, take flat start. We have already discussed what is meant by flat start. So, then therefore, we need not discuss it, and initialize let us say k. This is the iteration count, k is here, we must say that it is iteration count. So, this is the iteration count. Now, here only one very minor point which needs to be discussed. We have already seen that when we say that we are taking flat start. So, for these PV buses, we take the magnitudes as the specified voltage, and for the PQ buses we take the magnitude as 1.0 per unit, but for all these buses we take the angles to be 0. So, then therefore, in this rectangular coordinate for this PV buses, EI would be equal to nothing but the specified voltage magnitude, Fi would be 0 because this angle is 0, and for all these PQ buses EI would be equal to 1.0 and the Fi would be 0. So, this is the only thing we need to understand. Now, then for I is equal to 2 to n, calculate Pik is equal to j is equal to 1 to n. So, Eik, then Ejk, Gij minus Fjk Bij, Fjk Bij minus Fik, sorry, plus Fik Ej Bij plus Fj Gij, Ej Ejk Bij plus Fjk. There is some small mistake here, everywhere there is a mistake. This should be all, k minus 1, 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 k minus 1. So, when we are evaluating Pik, so then therefore, we need to use the previously known value, the last known value of all these voltage real and real part in this expression. Then calculate delta P vector as P2 specified minus P2k, P3 specified minus P3k, dot dot dot, Pn specified minus Pnk. Then what we do for I is equal to m plus 1 to n, calculate Qik is equal to j is equal to 1 to n. Then we Fi into Ej Gij minus Fj Bij, Fi into Ej Gij minus Fj Bij. So, Fi Ej Gij minus Fj Bij, then Ej Gij minus Fj minus Ei Ek Bik plus Fk Gik minus Ei k minus 1 Ej k minus 1 Bij plus Fj k minus 1 Gij. So, again the same principle, we are calculating Qik using the last known values of using the last known values of this real and imaginary part of the voltages. Then we form delta Q vector as Q m plus 1 specified minus Q m plus 1 k, then Q m plus 2 specified minus Q m plus 2 k, dot dot dot, Q q n specified minus q n k transpose. Then in the next step, what we do for I is equal to 2 to m, calculate V I k square is equal to E I k minus 1 whole square plus F I k minus 1 whole square, and form the delta V square vector as V2 specified square minus V2 k square then V3 specified square minus V3 k square dot 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 Vm, because we are doing only up to the PV buses. Vm specified square minus Vmk whole square transpose T. So in step 5, so what we have got? Different subvectors of this mismatch vector. So then after that we form delta m vector at kth iteration as delta p vector at kth iteration. We should also write k. We should also write here k, and we should also write here k. In fact, we should write here more elegantly. It is basically delta v k delta q k and delta v k whole square. We know that this dimension of this matrix rather vector is 2n minus 2 cross 1. So then therefore we can say that let delta m k vector is given by delta m1 k delta m2 k, it is all this component taken together, delta m 2n minus 2 k transpose. So then what we do? Then we calculate E I k at delta m I k for I is equal to 1 to 2n minus 2. Then we calculate E error at k as max of E1 k, E2 k. Please remember at this in this step everything is positive. So there will be some maximum quantity which would be indeed a positive. So we take the maximum of them. If error k is less than some epsilon, then stop else go to step 10. What we do in 10? We evaluate matrix J, with the vector of E and F known at k minus 1th iteration. So, we evaluate this matrix J with this vector E and F known at k minus 1th iteration. This is not minus, this is actually, this is not really minus, this is actually, this is a vector notation here, this is a vector notation here, and this k minus 1 denotes that this vector E is known corresponding to k minus 1th iteration, and this k minus 1 denotes that this vector F is known at k minus 1th iteration. And then what we do? Calculate delta x vector k as J inverse into delta m k, then update as x k is equal to x k minus 1 plus delta x k, and go to step 2. And here we should write initialize, and when we do initialize, then after taking flat start we actually know what is x vector is known. And what is x vector? X vector is vector E and vector F. So, then therefore, we first take the flat start. From here x vectors at the initial condition, that is the some 0th iteration is known, and after that we start our operation. So, after we take this initial condition, this is known. So, then therefore, after that we straight away keep on doing this iteration. After that it is straightforward, we calculate delta p k, we calculate delta q k, we calculate delta v k square, we form this delta m matrix, then we check for convergence. If it is within some threshold value, then we stop, we say that it is, that my solution is obtained. Otherwise, we evaluate this Jacobian matrix, take its inverse and calculate this correction vector, add that correction vector with the previously known x vector. X vector is nothing but the solution vector. Remember, when k is equal to 1, it is 0. So, then therefore, we know this, and we have just now calculated. So, we know this, and then we go to step 2, and here also go to step 2. Here also we should write k is equal to k plus 1 and go to step 2. So, this is the very basic algorithm of this Newton-Raphson rectangular method. In this algorithm, you must have noticed that we have not considered the case when there would be some violation of the reactive power limits of the generator. So, in the next lecture we will be considering that, and then also we will be looking at a simple example for Newton-Raphson rectangular method. Thank you.